Hello everyone. Today we're going to go over how to represent decimals, numbers as ones and zeros. And we're going to go over how to use a sequential multiplier to do multiplication in hardware. Before we can do multiplication or write a circuit to do multiplication, we need to understand how to represent numbers as ones and zeros so we can know what the inputs will be to the circuit. So fortunately this process is very simple. So let's go over, we're only going to go over two brief examples before showing how to use the module. So suppose we have 17.5 and we want to represent that with 18 bits, with one sign bit and 6 fractional bits. The first step is to find what positive 17, the integer part, is. And to do that, you just use this common algorithm where you divide by 2, record the remainder, divide by 2 again, record the remainder. And then once you have all your remainders, you append a 0, and then record the numbers as your final answer. So for this, 17 divided by 2 is 8, remainder 1, so we write a 1. 8 divided by 2 is 4, remainder 0. 4 divided by 2 is 2, remainder 0. 2 divided by 2 is 1, remainder 0. 1 divided by 2 is 0, remainder 1. We append a 0. Then going up this way, we see the answer is 0, 1, 0, 0, 0, 1. So that's positive 17 in binary. Then to find 0.5 in binary, you use a common algorithm where you take the fractional part, you multiply it by 2, get the new number, multiply the fractional part to get the next number, and you repeat the process, and then you record the digits from the second one down. So we have 0.5 times 2 is 1.0. We write 1.0. And then the fractional part times 2 is 0. So we get 0.0. The fractional part 2 is 0, so it's just always going to be zeros after that. And then the third step is going to be to combine and take the 2's complement if necessary. So we combine this part with this part to get this. Because it's positive 17, we do not need to take the 2's complement, we can just use it as is. But we need to sign extend to make it fit the format, because we want it to be 18 bits with one sign bit and 6 fractional bits. For this, we need to add 2 zeros to make it have 6 fractional bits, and then we need to add as many zeros as needed to make it the whole thing be 18 bits. And when we do that, we get this. So example 2, the same algorithm gets used here, and here, and here, and then since it's negative, we have to take a 2's complement. I'm not going to go over how to take a 2's complement since that's something you should already know how to do. I'll probably make a video on that later if I haven't already. So you can refer to that if you need. But anyway, once you take the 2's complement, you get this. Then you need to sign extend it to get this. So for our Verilog multiplier, we're going to have input for operand A and input for operand B, a start pulse button, a product bus, and a done pulse. The inputs A and B are going to be just a list of ones and zeros. So this might be input A. We have this long thing going there, and then this might be input B. Okay. So this is the source file. This source file has been verified to always work. So you don't need to worry about modifying this, you just need to learn how to use it. So to use it, you define the width of your input and how many fractional bits. So over here it's matching the exact format of our example. So with 18 bits, so it's 18 bits long. So we set the data width to 18 with 6 fractional bits. 6 fractional bits. Once we do that, we can apply numbers. So we're going to use A and B, the exact same operands we calculated earlier. So it's this one right here, and this one. And then there's another case here where we do 100 or 100, and this one is not going to work because it's going to overflow because we're not using enough bits. But this one will work because it's within range. And then I'll go over how to fix this problem in a few moments. So I'm going to run simulation. So because we chose to have our input be in the format with 6 fractional bits, we do this. So to start, we change A and B to be the binary values we want. In binary, it's this, and that binary number is the same as this, but let's choose the radix back to. So at the start, we update A and B to be what we want to multiply. Then we make a start pulse. Then sometimes later it updates the output, and then a done pulse. 17.5 times negative 45.75 is negative 800.625. So that worked. Let's go farther, simulate more. Then the next one happened. 100 times 100 is not 1808. That's wrong. And the reason why it's wrong is because we ran out of bits. To properly use this module, you need to know how many bits to do. Let's do 32, that's enough. So let me choose this to 32, 2. So we need to add a bunch of zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You need to add a bunch of ones and zeros to sign extend it. Okay, for 32 bits. Bits are there, 32. Okay, so that's 32 bits long then, okay. So now let's change all of them to be 32 bits long. So now that we changed it to have more bits, the second one will work correctly this time. Settings. Still using only 6 bits of fraction. Okay, this is still right. And then now this second one is correct. So 100 times 100 is this value here. So yeah, it worked now. So that's how you use this source file, and that's how you can multiply any binary number of your choice. you wanted to multiply 57.2 times 91.4, you would shift in your correct operand once you do your binary conversion. Then you would apply a start pulse, wait some time, and then see what the output is, all while making sure you have enough data width and fractional bits. So there you go. That's all you need to know for how to do multiplication in Verilog using this multiplier.